Section 6.2 is on applications of right triangles. Our objectives are going to be to solve right triangles and to solve applied problems that involve right triangles. Topic 1, solving right triangles. Quick review, a right triangle is a triangle where one of the angles is equal to 90 degrees, and in this diagram, the angles are labeled with the capital letters A, B, C, and then the sides are labeled with the small letters A, B, C. Angle A is across from side A, angle B is across from side B, etc. That's one of the common ways to name a triangle. Okay. Based on what we compiled in the last section, along with the Pythagorean Theorem, we can pretty much solve any right triangle. By solving, we mean finding the lengths of all the sides and the measures of all the angles. Given only a few specific pieces of information to start with. Alright, so in order to make solving right triangles easier, it makes sense to develop a good system. So if we know one of the acute angles, okay, then how do I find the next? So the two acute angles in this triangle are called A and B, and because we already know that C is 90, we don't need to find C. It's a right angle, it's 90 degrees. So that's a known quantity. All the angles in the triangle have to add up to 180. Since that one's already 90, these two have to add up to 90. So we know that A is equal to 90 minus B, and vice versa. B is also equal to 90 minus A. So if you know either one of them, A or B, you can solve for the other one by subtracting from 90. If we know the two shortest sides, well, we can use the Pythagorean Theorem to find the longer side. So we can use A squared plus B squared equals C squared, and we can solve for that missing side. So the missing side in this case would be C squared. If we know the hypotenuse and one side, well, then I would have the same thing, A squared plus B squared equals C squared, but this time I'm looking for one of the sides. Let's say it's B, and so I would subtract A over, solve for B using the square root. So it doesn't matter which side I'm looking for. If I know two sides, I can find the other side. So if I know two angles, subtraction gets me the third. If I know two sides, Pythagorean theorem gets me the third, no matter which two I know. If I know any two sides and want to find an angle, that's where I can use my trigonometric ratios. So for example, I know that the sine of angle A, for example, is equal to the ratio of opposite, which is little a, divided by hypotenuse. And so if I wanted to find A itself, A would be the arcsine of the ratio little a over c, and then etc. for the other 6 possible trig ratios. We're going to work on the primary 3, so we're going to say etc. for cosine and tangent. Because the other 3, cosecant, secant, and cosecant, are just reverses of sine and cosine, so we may as well use the primary 3, and then we'll be able to relate AC, AB, BC, whatever it happens to be. Excellent. All right. So that was our quick review there. Let's take a look at doing that in a few of these examples. Example 1, I want to solve each of these following triangles. Okay, so I have C, I have 45 for angle B. So angle A is going to be 90 minus 45, which is 45. Since I already have a 45-degree angle, the two angles need to add up to 90. I can take 90 minus 45 and get 45. Now I know all 3 angles. I only know one side. I do not know 2 sides. So I'm going to have to use a trigonometric ratio to find one of the sides. Once I have 2 sides, I can use Pythagorean theorem to get the third. Okay. I'm going to use the angle that I already had with the 10. And so in terms of excuse me. So in terms of B, angle B, let's go ahead and find side B first. So side B would be opposite So I'm going to use the sine opposite over hypotenuse. So we're going to use the sine of 45 degrees, that's capital B, is equal to the ratio of opposite, which is little b, divided by hypotenuse, which is 10. Now, the sine of 45 is known, it's a known angle, so instead of getting a decimal here, I can calculate that exactly as the square root of 2 over 2. Then I can multiply both sides by 10, 10 square root of 2 over 2, or reduce that to 5 times the square root of 2. Okay, so b is 5 times the square root of 2. I only have one piece of information missing. Now we're going to go ahead and find side A. Now I could use a trigonometric ratio again, or I could use the Pythagorean Theorem. The trigonometric ratio is going to come out the same. Actually, I already know the answer is 5 square root of 2, because if the two angles are the same, the two sides have to be the same. This is an isosceles triangle. But just to verify, let's go ahead and use the Pythagorean Theorem to make sure that that comes out. So we have a squared plus 5 square root of 2 squared equals 10 squared. A squared plus b squared equals c squared. So a squared equals, I'll just put a squared plus first. 5 squared, that's 25, times square root of 2 squared, that's 2, equals 100. So a squared plus 50 equals 100, subtract 50. A squared equals 50. And so a is the square root of 50, which separates into the square root of 25 times the square root of 2. So it does give me a equals 5 times the square root of 2. So these are all the things that I solved for. So a is also 5 square root of 2. Okay. Now, very similarly, I could have set this up as sine of a equals little a over 10 and done it the same way as I had before, since I knew that angle. But just to check out all three of our methods, there we go. Let's take a look at the next one. In this case, I have a 30-degree angle, and so angle F is going to have to be 90 minus 30, which is 60 degrees. So this angle is 60 degrees. So it's a 30, 60, 90 triangle. Okay, I don't know one on the side, so I get to use some trig again. Let's go ahead and use angle D, and we'll find little d. So I'm going to use the sine of 30 degrees equals little d divided by 6. I don't need to approximate the sine of 30. I know it from my chart. The sine of 30 degrees is half equals d divided by 6. And so if I multiply both sides by 6, I get 6 divided by 2, or 3, for d. So d is 3. Okay, so 60 degrees, 3, and then I can use either the Pythagorean Theorem or the Trigonometric Ratio to find f. I used the Pythagorean Theorem last time. I'm going to use a Trigonometric Ratio here, just for fun. Okay, so cosine of 30 degrees is adjacent, that's little f, over hypotenuse, which is 6. I'm choosing cosine of 30 instead of sine of 60 because I like to use the numbers that are already present in case I made a mistake with the 60. If I can't subtract 90 minus 30, maybe I made a mistake there. So I know that the cosine of 30, the one that's already written for me, will be f over 6. Looking at my chart, the cosine of 30 degrees is the square root of 3 over 2 equals f over 6. Multiply both sides by 6, that's 6. Square root of 3 over 2 equals f, reduces to 3, square root of 3 equals f. So f is 3 square root of 3. And now I have the triangle solved because I know all of the sides. 3 square root of 3, and 6, 30, 60, 90.